Okay, we're down to the last two chapters. Because I forgot about fall break when I did the syllabus originally, I had an extra chapter on there, chapter 16, but we're not going to do that. So we will do chapter 11 this week and chapter 12 next week, and then you'll have the final week just to take the final exam. So this is kind of the point of the whole course, capital budgeting. And so in this chapter, we're going to learn the tools of capital budgeting. So what is net present value, IRR, MIRR, and so forth. And then in chapter 12, we're actually going to apply these tools to different projects. So what is capital budgeting? Capital budgeting is the big ticket spending that companies do. So it's the analysis that we do when we ask the question, are we going to invest in this piece of equipment? Are we going to buy this company? Are we going to expand into China? And so any kind of big spending is called capital budgeting. And the key factors of capital budgeting are that the decisions are long-term, so they tie up your money for a long time, and they cost a lot of money. So it's really important that you get the capital budgeting analysis right, because if you don't, you'll cause this firm to waste lots and lots of money. So capital budgeting is really, really important to the success of the firm. And it's the way that we maximize shareholder wealth. By choosing the right projects with the highest net present values, that's how we make the firm more valuable. So what are the steps in capital budgeting? We estimate the cash flows associated with the project, so all the cash flows associated with the project, and in chapter 12 we're going to talk in depth about those cash flows. We assess the riskiness of the cash flows so that we can come up with the appropriate risk-adjusted discount rate, and then we use that rate to discount the cash flows to the present and find the net present value or the internal rate of return. And the ultimate decision, if the NPV is positive or the IRR is greater than the weighted average cost of capital, it's a good project. All right, so what's the difference between independent and mutually exclusive projects? So very simply, independent projects means that projects, the cash flows are not affected by the acceptance of the other, but it also means that you can accept any independent projects. So most companies have a whole array of projects that they are evaluating, and they're trying to decide which of these projects should we invest in. So independent projects would say, if the NPV is positive, go ahead and accept it. It doesn't depend on the other projects. Mutually exclusive projects would be when you're evaluating perhaps two different ways to accomplish the same goal, and so you're not going to do both, you're going to do one or the other. And so that's an example of mutually exclusive. And it makes a difference in the evaluation if the projects are mutually exclusive or independent. So very simply, you already know how to do NPV because we've been doing it in other examples. I think we used the NPV function when we did the time value of money and we had uneven cash flows. So you already know how to do this. So the net present value is simply the sum of the present values of all the inflows and outflows associated with the project. So here's two projects that we're going to look at, Project L and Project S, and ignore this for right now. So the project cash flows associated with L are these, and associated with S are these. So we want to calculate the net present value, and to do that we need a discount rate. So the weighted average cost of capital is what we're going to use to discount these projects. Now remember, we just did the weighted average cost of capital in the last chapter, and so this represents the hurdle rate. Projects have to earn more than the weighted average cost of capital to be good. Okay, so we're going to use 10% as the discount rate to discount these cash flows. Now I'm going to bring up my little trusty calculator here and do it on the calculator. So there's the cash flows. All right, so I'm going to clear all, make sure nothing's in the memory, and it's set on 1p per year. So 100 is my cash flow 0, and so I just click on this calculator, the CFJ key, and a 0 comes up to let me know that was cash flow 0. And that was supposed to be negative, so let me clear all and start over. All right, so I have 100 negative is my cash flow 0, and then 10 is my cash flow 1, and the 1 pops up there. 60 is my next cash flow, and 80 is my next cash flow. Okay. Now, to find the NPV, I have to give it a discount rate, and so we said that 10 was the weighted average cost of capital, and that's the interest rate per year, so I click on interest rate per year, and then I'm going to calculate the NPV right here, so I do orange key NPV, and I get 18.7829, or 0.79, they rounded up, okay? Now, if you're doing this on Excel, this is an oddity in Excel, I don't know why it is. But so when you use the NPV function in Excel, it assumes that the first cash flow it meets is a time one cash flow. So you don't want to highlight the whole array in Excel. So these are actually easier to do on your calculator than in Excel. But if you want to use Excel, the NPV function, and so you put the rate, click on the rate, highlight cash flows 1 through n, in this case 1 through 3, hit enter. Then you have to go back up to the equation line and manually add plus cash flow 0. Okay, so I would add my plus negative 100 to get the NPV of 18.7829. Okay, let's do another one. So this is project S. And now again, I'm going to clear all, because I want to get, if I don't clear all, it retains what's in the memory. Okay, and also you want your calculator set on 1p per year because it will affect even this using the cash flow keys. So let's do project S. So 100 is negative, cash flow 0, and 70 is cash flow 1, 50 is cash flow 2, and 20 is cash flow 3. And they both have the same weighted average cost of capital, right? Yep. So we're going to input 10 again is my interest rate. And again, I'm going to calculate the NPV, 19.98, okay? So that's all there is to it. Now, okay, let me just show you this while we're here. So all the cash flows are stored, so if I want to calculate the internal rate of return, I just hit the internal rate of return key right here. So I'm going to do orange key, IRR per year, and you saw it running, it was thinking there, and so my IRR is 23.56%. Okay, so just kind of file that away in your mind. The internal rate of return is the interest rate that the project provides. So it has a positive NPV of 19.98. What that means is this project earns, it recovers the cost, the $100 at time 0. It earns a 10% return on that $100 investment over the 3 years, plus $19.95 left over. So why does it do that? Because the IRR is greater than the WACC. So if the internal rate of return is greater than the WACC, that leads to positive net present value. Okay, so the two are related. There are two different ways of evaluating if a project is good. And so here's a summary of what we just did on the calculator. Okay, so NPV is really easy to interpret. It's money, and more money is preferred to less. And so the net present value is the present value of the inflows minus the cost. Okay, again, on the calculator, it's really straightforward. In Excel, you've got that one extra step. But so what NPV means is it's a gain in wealth. It increases the size of the firm by the amount of the NPV. So if projects are independent, except any that have the NPV greater than 0, right? Because anything greater than 0, it covers the cost plus the required return, the 10% return. So if there's money left over, it's earning above and beyond the required rate of return. That's a good thing. If projects are mutually exclusive, take the one with the highest NPV because more money is better than less. And so in this example, except S, if it was mutually exclusive because it had the higher NPV, let's just go back and look at those. So S's NPV was 19.98 and L's was 18.79. Okay, so if they were mutually exclusive, then we would accept S, otherwise we would accept both of them. So the internal rate of return that I found, conceptually the internal rate of return is the interest rate that makes the NPV be 0. Mathematically, that's the definition of the internal rate of return. And conceptually, it is the return that the project provides. And so enter the cash flows into the cash flow register and press IRR like we just did. And so the IRR on L was 18.13 and on S was 23.56. So similar to NPV, if you are choosing between projects, if they're mutually exclusive, you're going to pick the one with the higher or the higher IRR. What do you compare IRR to? The WACC. So as long as the IRR is greater than the WACC, it's a good project. These are both good, and higher IRRs are better. So how's a project's IRR similar to a bond's yield to maturity? Actually, they're the exact same concept. So the yield to maturity on a bond is the return on the bond project. And so suppose you have this bond, you might want to solve for this and calculate the yield to maturity, but that's the exact same concept as the IRR on a project. Okay? So if the IRR is greater than the WACC, then we accept the project because that means the NPV is positive. If the IRR is less than the WACC, we reject it because that would be a negative net present value project. If they're independent, we accept everything with the IRR greater than the WACC. If they're mutually exclusive, we take the one with the higher IRR. Okay, similar to the NPV. All right, so the NPV profile is a picture. It's a graph of the NPV at different interest rates. Okay, and so here we have different weighted average costs of capital, and so you can plug your cash flows into your calculator, and then you can put in zero for the interest rate and get the NPV. Then just put 5 interest rate NPV, 10 interest rate NPV, and so you can calculate the interest rate at all these different WACCs. Okay, and we do that for both, and that's going to allow us to draw a picture of the NPV profile, how the NPVs are on the y-axis and interest rates are on the x-axis. So what happens to the NPV as the discount rate goes up? And so here, the point that the line crosses the x-axis is the internal rate of return. So this is the net present value profile for the long project, project L. Okay, now here's both of them. And actually, if we go back and look at this, if we look at the cash flows, we see at a 0% discount rate, L has a higher NPV, and at 5 it does, but at 10 they switch. And at 10, the NPV is higher for S, and it stays higher than at the other discount rates. So there's only one IRR. Okay, the IRR is the point where the project crosses the y-axis. So there's only one IRR. There's only one internal rate of return for a project. But the NPV depends on the discount rate. And so when you're choosing between projects, the relative ranking can change if the cash flows are not identical to each other. And so that's what we have here. At low interest rates, L is a better project, and at high interest rates, S is a better project. So that brings up a question then, what is the crossover point at what's the interest rate at which they change? And that's the crossover point. So how do we find the crossover point? Well, that's what these delta cash flows back here, not there, here. That's what this was for. So to calculate the crossover rate, we subtract S from L. So negative 100 minus a negative is 0. 10 minus 70 is negative 60. 60 minus 50 is 10, and this is 60. Okay, and we calculate the internal rate of return on these cash flows, and that is the crossover rate. Okay, so let me go back to where we were. Okay, so find the cash flow differences between the projects on 11.7, that's where we just were, and enter the delta cash flows in the cash flow register and press IRR. And so the crossover rate is 8.68% rounded to 8.7. Okay, so we just input the cash flows just like we did for the other one. Yeah, so I don't think I have to do that, but you do that. Input your cash flows, and then just and so you don't have to. Okay, mistake students always make. To find the IRR, we don't need to put in a discount rate. We don't need to put in that 10% WACC. The IRR doesn't have anything to do with the WACC in terms of its calculation. So all you have to do is enter the cash flows and then press IRR, and you'll get the internal rate of return. And so again, what that tells you is this is the place at which they switch. If your cost of capital is below 8.7, choose L. If it's greater than 8.7, choose S. That's what the crossover rate tells you. Okay, so why do they cross? Well, in this case, they crossed because the pattern of the cash flows was different. We had a timing difference. They can also cross if the size of the projects is different, but this one we didn't have that because the size of the projects was both $100 million. Okay, and so if we look at what's happening here, so they both cost the same, they're the same size, but Project L has little cash flows early and they get bigger. S has the big cash flows early and they get smaller. So if you think about the time value of money, these cash flows out in year 3 are discounted more heavily, right? They're being discounted at 1.10% to the third. And so the higher the discount rate, the faster these far out cash flows diminish. And so that's why at low interest rates, the fact that 10 plus 6 is plus 80 is 150, and this is 140. So L provides more total cash flows. So at low interest rates, that makes L dominate, and it has a higher NPV. But at high interest rates, the fact that L's big cash flow is 3 years into the future makes the NPV be less. Okay, so whenever your cash flows have different timing patterns like that, or different sizes, you're going to get a change in NPV, and so it's good to know where does that happen, what is the crossover rate. Okay. Now, NPV and IRR are conceptually two different methods that we could use to evaluate projects in capital budgeting. NPV will always give you the right answer. IRR has some problems. So one difference between the two methods is the reinvestment rate assumption. So when we get those cash flows, the 10s, the 20s, the 80s, NPV assumes that you get those cash flows and you reinvest them at the cost of capital, which in this case is 10%. IRR assumes that the cash flows are reinvested at the IRR. Now, if we think about which is more likely, if you've got a bunch of projects and you rank them according to the IRR and you choose the best project first, then there's not going to be the opportunity to reinvest those cash flows at 19%, right? Because you just took the 19% project and there aren't any more. And so the IRR assumption actually overstates what you can reinvest the cash flows at, and that has the effect of overstating what the IRR actually is. So you might say, then why does anybody do IRR? And I would say that's a really good question, because there's other problems with IRR, as we're going to see in a minute. But what happens in real life, I mentioned in the cost of capital chapter that is where we're finally actually getting to some kind of big finance theories, that there's very often a difference in practice and in academics. And of course my take is that the practitioners don't know what they're doing. But what I hear from practitioners is, I don't know what NPV means, I know what IRR means. And what they're saying there is false, but what they're saying is, I think I know what interest rates mean, and I know an interest rate of 19% is a good interest rate, so I'm going to take that. I don't know what NPV means. Well, NPV is money. And so the flaw in that argument is IRR is not adjusting for the risk. And so maybe that project has a 19% return, but the risk required on that project is associated with a 24% cost of capital. So in that case, it's going to be negative net present value. And assuming that you know 19% is a high rate, so you accept the project, is going to lead you to make a wrong decision. Okay? So that's one problem with IRR. Another is this reinvestment rate assumption. And so because people like IRR, the MIRR is a tool that we can use to make IRR better. And so you can use this tool in a couple different problems, but so this is an example of solving the reinvestment rate problem. So this is Project L again, and so we've laid the cash flows out on a timeline. I would recommend that when you do any problems now, from now in Chapter 12, you draw a timeline like this, because the problems are going to get complicated and they're going to have multiple cash flows in years, and so you need to start drawing timelines and just laying out your cash flows, what happens in 0, what happens in 1, and so forth. To calculate the MIRR, we take any positive cash flows to the future, compounding them at the cost of capital. So this is 60 times 1.10 gives me 66. This is 10 times 1.10 squared gives me 12.1. Okay, or you can put in PV, N is 1, I is 10. What's the future value? However you want to do it. But we want to get all of our positive cash flows out here at the end, compounding interest at the cost of capital, and then we want to bring any negative cash flows to time zero. Well, in this problem, we only have one, and it's already there. But if we had a negative cash flow here somewhere, we would discount that negative to time zero and add it to this to get all the negatives at time zero, all the positives at time 3. And so if I bring my calculator back now, so I'm going to clear all again. So to calculate the modified internal rate of return now, I've only got 2 cash flows. So I'm going to say 100 negative. Negative is my present value, and 158.1 is my future value. N is 3, and so I'm solving for the internal rate of return. Now in this case, I use this key as the internal rate of return because I'm using my time value of money keys. And so I calculate the internal rate of return. And so why isn't it calculating? We are not knowing why it's not calculating. Maybe it didn't take my N. There we go. I don't know, 16.5%. Okay, so 16.5% is the modified internal rate of return. And if you remember, the internal rate of return on this one is 18.1, I think. And so the modified internal rate of return is less because we're reinvesting the cash flows at 10% instead of 18%. Okay? So again, compound all positive cash flows to the future, to the last date, bring any negative cash flows to the present, and then just input present value, future value, N is 3, solve for I. And that's your modified internal rate of return. Okay? Now, so it assumes the reinvestment at the opportunity cost of capital. It also avoids the multiple internal rate of return problem. And so what's the multiple internal rate of return problem? Okay, whip out your calculator and try this. So a project has cash flows of negative 800, 5,000, and negative 5,000. Okay, so put those cash flows into your calculator and put my calculator back. We'll see what happens. Okay, so again, clear all. So we've got 800 negative is cash flow 0. Oops. Start over. Alright, 800. The real calculator is not this touchy. Okay, cash flow 0. Alright, 5,000 is, sheesh. Come on. Aha, yay, is cash flow 1, and then 5,000 negative is cash flow 2. Trust me, that's true. I'll move the calculator in a second. Okay, so I want to calculate the internal rate of return, and so my IRR is right here on this key, so I'm going to hit orange key, internal rate of return, and it's going to say not found, or no solution, or something. You'll get some sort of an error message. And so the problem is, let me show you the graph before we come to the solution. So here's the NPV profile for this project. Now remember I said the IRR is the point at which the profile crosses the x-axis. And so what you have here is that this is crossing at 2 different points. So there's 2 IRRs. And so it's not that it was not found, it's that the calculator doesn't know what to do. So your calculator is saying not found. So on my calculator, what it says is input a guess. And so if you input a guess, so let me first say, so when you're calculating the IRR, what your calculator is doing is it's trying different interest rates until it finds the one that the NPV is 0. When I first started teaching finance 150 years ago, we didn't have financial calculators like this, and so we had to actually do it by hand and try it. But so now your calculator does it for you, and that's why you see it thinking for a minute, is because it's actually physically trying out different interest rates, searching for one that makes the NPV be 0. So in this case, it did that, and it freaked out and said, oh my gosh, there's more than one, I don't know what to do. And so if you put in a guess, so we're going to say, okay, I'm going to store a guess. So I'm going to store 10, if I can get it to take 10. I don't trust that. Let me go back and get it to take a real 10. So 10. And we use the store key. And so the store key is right here. And so if you click orange, store that, and then click IRR, it's going to search just around 10%. And it comes up with IRR of 25%. And so then I say, okay, pick a number far, far away from 10. So I'm going to say, okay, search also around 300. And so I'm going to store that. And then I'm going to click on IRR. And it's running, and it found 400. And so I was able to find these 2 points. So what's going on? Well, so let's go back and look again at the cash flows of this project. So at really low interest rates, the NPV is negative. Let me go back and look at my profile down here. Make sure we're doing the right problem. Oh, that we're not doing that problem. We're doing a different problem. We're doing this one right here. Okay. So at really low interest rates, like close to 0, and for a while, this has a lower present value than this, right? Because it's discounted at 1.1 to the squared, and this is discounted at 1.1. But so basically, at 0% interest, these wipe each other out, and the NPV is negative 800. So at 1%, 2%, 5%, the sum of these two is turning positive, but it's not enough to overcome this. So let's go back to the profile. So that's what's happening here. At interest rates between 0 and 25%, it's negative because of how the cash flows are. At interest rates above 25%, that negative cash flow in time 2 starts being worth less and less and less, and the NPV actually turns positive. At interest rates of 400%, that first cash flow basically is worthless because interest is so high, and so the NPV turns negative again. Okay, so we can use the MIRR method to figure out an IRR if we wanted to on this. I would just say calculate the NPV and be done with it. And the NPV at a reasonable interest rate of 10% is going to be negative. But so you could, if you wanted the IRR, bring this second cash flow, discount this 2 years to time 0 and add it to this, and compound this guy to the future, and then solve for present value, future value. What is the IRR? So as I said, the NPV is negative, and that's easy and that's correct. But anyway, that's how you calculate the MIRR and why you would. So, and then I just explained why there's multiple IRRs. Okay? So the MIRR is 5.6%, and so after all that work, you say, okay, 5.6 is less than 10, so don't do it. Well, you got that same answer by finding out the NPV was negative. So it's just because people like IRRs and think they know what they mean. My advice is forget IRR and just use the NPV. Okay, the payback is a method that should never be used, but again, you hear people talk about it. And I say should never be used. The one place where it might be used is in a small business where they do not have access to all the money they need. And so then payback becomes important. But so payback is simply how long does it take me to get my money back? And the reason I say it should never be used is because payback ignores the time value of money, and it treats all these cash flows the same. It also ignores the risk of the project. But so if we want to calculate the payback, we just kind of accumulate here. So this thing cost $100. So after 1 year, if we earn 10, we have not recovered 90 of the cost. So if we earn 60 in the second year, then 60 from this means we haven't recovered 30. And then here in year 3, we're going to break even. So what's our payback? It's 2 plus 30 divided by 80. So this is standing for 3/8 of the way through year 3, we're going to recover our cost, and so the payback is 2.375 years. The payback on Project S, because it had bigger cash flows early, was only 1.6. So the decision rule on payback is faster is better. But like I said, if these projects had differential risk, it ignores that, and it ignores the time value of money altogether. So it's easy. Sometimes companies use it as an initial screen, but I would say don't even use it as an initial screen. The other problem with payback is it ignores the cash flows that come after the payback period. So what if there was some big cash flow out here in time for a $1 million cash flow? It would ignore that. It would just say, well, we pay back in 2.37 years. Okay? Now, again, just like MIRR is a way to make IRR people happy, we can calculate the discounted payback, but this is a whole bunch of work for nothing. And so in this case, I'm finding the present value of this one, the present value of this one, and I'm doing the payback calculation the same way. So when I account for the time value of money, the payback is actually longer, 2.7 years. So that's just kind of to show you what discounted payback and payback are. They are not methods that should be used. We should only use methods that take into account the time value of money, and those are the NPV, the IRR, and the MIRR, and of those, NPV will always give you the right answer. Okay, I'm going to do another narrated something and work some problems, because I want you to get practice and maybe watch me work some problems.